So now we're going to take a look at derivatives of those exponential and logarithmic functions that we started to talk about in the last section. We'll start with the exponential functions, and this is part of the reason why e is my second favorite number. If you're working with the function e to the x, the derivative of e to the x is e to the x. It actually doesn't change. It's a very cool function that is in fact its own derivative. So this is kind of one of those trick ones, which is, on the one hand, it's nice. I think it's easy to remember, but on the other hand, I will try and trick you with this one, and I'll show you some of the tricks in these examples here. So first of all, f of x, part A here, I have f of x equals e to the x plus 5x cubed minus 2x plus square root of x. If you have anything like this square root of x, I'm going to take just a moment to rewrite that so that I have f of x equals e to the x plus 5x cubed minus 2x plus x to the 1/2, just so that I have that written as x to some power, and I can use my power rule on this guy. And again, notice I haven't actually taken the derivative. All I did was rewrite it, so I still need to use my power rule. So f prime of x, when I take the derivative of e to the x here, the derivative of e to the x is just e to the x. Plus everything else is going to act sort of the way we would expect it to. So the derivative of 5x cubed, that's going to be 15x squared. Derivative of negative 2x, that's going to be minus 2. Plus x to the 1/2, derivative of that term, so I'll have 1/2 x raised to the negative 1/2 power. We could leave our answer like that, or we could rewrite this as e to the x plus 15x squared minus 2 plus 1 over 2x to the 1/2 power. Either one of those would be just fine. So for the most part, it doesn't really, I don't think it has a dramatic impact on how we take derivatives, but it is something that we will have to keep an eye out for, because in examples like in part B right here, I am going to try and trick you. Like I said, here I have f of x equals x to the 7th minus x to the 5th plus e to the 3rd minus x plus e to the x. So nothing here looks like it really needs to be rewritten, so I can jump straight to taking the derivative. So x to the 7th, I'm going to use the power rule there. I should have 7x to the 6th for my derivative. X to the 5th, again, that's another power rule, minus 5x to the 4th. Plus e to the 3rd, that's another power rule, right? And that's when I say, no, it is not. Be careful. This is e to the 3rd. Remember, e is a constant. E is a constant. So when I say e to the 3rd, what this guy really says is e times e times e. I don't know what that is. It's going to end up being some ugly looking decimal, but it's going to be a constant. So I have really a constant to the 3rd power, which is still a constant. This term right here is just a constant. What's the derivative of a constant? Derivative of a constant is 0. So just be very, very careful. I may throw in e to some power right there, in which case we just need to be careful that we recognize that as a constant and not something that we're going to use the power rule on, because the base e is a constant rather than a variable like we have x here. So we can continue on. Derivative of negative x, that's going to be negative 1. And then derivative of e to the x is plus e to the x. If you don't want to write this plus 0, that's fine. I would expect most of us to probably write our final answers as 7x to the 6th minus 5x to the 4th minus 1 plus e to the x. So there is my derivative. Next up, let me do this in a different color. How about we do this in green? Part C, I have f of x equals 4e to the x minus 7x squared plus 1 over x. Again, this guy, that 1 over x, I probably want to take a moment just to rewrite that expression. So let's do that. F of x is equal to 4e to the x minus 7x squared, plus that's really x to the minus 1 power. So again, I haven't taken the derivative. All I did was rewrite this expression. So now I need to take the derivative, f prime of x. And the hardest part about this guy is going to be this 4 right here. A lot of us want to say that the derivative of 4e to the x is just e to the x. That would be wrong. Because 4, remember, this is 4 is a constant multiple right here. I have 4 times e to the x. I don't have 4 plus e to the x. I don't have 4 minus e to the x. I have 4 times e to the x. So when I look at 4 times e to the x, 4 is a constant multiple. It's not really going to have a dramatic impact on my derivative. What's the derivative of e to the x? Well, the derivative of e to the x is really just e to the x. That 4 just comes down. Now, like I said just a second ago, if you had 4 plus e to the x, that would be an entirely different story. If I wanted to take the derivative of this, I would have 0 plus e to the x. So just be very careful when you have that constant multiple. It's really not going to have a dramatic impact on your problem. It's just going to tag along to the next step. That's really never going to drop off no matter how many times you take the derivative. So I have 4e to the x as the derivative of my first term, minus here 14x to the first power, minus 1x raised to the negative 2 power if I use my power rule. And you could leave your answer like this if you wanted to, or if you liked positive exponents, we could say 4e to the x minus 14x minus 1 all over x squared. So either one of these would be perfectly acceptable as a solution. So again, just be careful with that constant multiple. Remember, that's 4 times e to the x is not 4 plus e to the x. Lastly, this guy right here, I want to take the derivative f prime of x. It doesn't look like anything needs to be rewritten. Well, 3x to the e, derivative of 3x to the e, that's got to be 3x to the e, right? And that's when I say no, it is not. Be very careful with this one. I tried to trick you again. Notice that x to the e, that's a whole lot different than e to the x. I'm going to handle this in a different way. So, okay, I need to think about this. Remember, we said earlier, oops, don't want to erase that, I want to highlight it. E is some constant. Remember, e is some constant, which means that e is some number. So I really have here, I have 3x to the nth power, right, where n is just some power. Essentially, I just need to use the power rule on this term. So what does the power rule say? The power rule says I multiply by my power, so 3 times e, x, and then I subtract 1 from my power, so I would have e minus 1. There's not really a great way to write that one, so I'm just kind of stuck with 3 times e times x raised to the e minus 1 power. So again, that's just what I'm stuck with here. I can't really do anything else. So that's just the derivative of this first term. Derivative of negative 2e to the x, again, we have a constant multiple of negative 2 right here. This is negative 2 times e to the x, so the derivative of that term will be minus 2e to the x. And then e to the fourth again here, just be very careful. This is e to the fourth. This is a constant to the fourth power, which is still just a constant, so the derivative of that last term will just be 0. We don't need to write that plus 0 if we want. We can just say, okay, there's our derivative. That's perfectly fine. So finding the derivative of e to the x is really not all that difficult. It's really just kind of paying attention to those trick aha gotcha moments that we need to kind of just keep an eye out for, because they will pop up from time to time. If I want to take the derivative instead of natural log, so if I'm taking the derivative of natural log of x, the derivative of that is 1 over x. So f prime of x is 1 over x. And in order to make full use of this derivative property right now, I'm going to rely on some logarithm properties. You may have seen these in college algebra, but just in case we haven't, it's been a while, maybe we've forgotten them, I want to talk about these logarithm properties. The first says if you have natural log of a times b, so we're multiplying two factors inside of a natural logarithm, I can expand this to say natural log of a plus natural log of b. So So I can kind of pull it apart into two separate logarithms. The second, very similarly, says if I have natural log of a divided by b, well, division is the opposite of multiplication, so I would expect this right-hand side, what's the opposite of addition? Well, subtraction, and you would be exactly right. Natural log of a minus natural log of b. Lastly, if I have natural log of a raised to the p power, so p is my exponent here. The way I sort of think about this is we can take this exponent and then we can bring it to the front. We can rewrite that as a factor. We can rewrite this as p times natural log of a. So I can kind of get rid of that exponent. I can rewrite it as a factor. So we're going to use these properties as we need to, if necessary, to help us take derivatives of some natural logarithms. So let's start here with part A. I have y equals 10x cubed minus 100 natural log x. When I go to take this derivative, y prime, 10x cubed, so that's just a regular old power rule. That's going to be 30x squared. Minus over here, again, this 100, this is really just a constant multiple. So that's just going to come down. It's going to tag along to the next step, 100 times, well, what's the derivative of natural log of x? Well, we said that derivative was 1 over x. So I have minus 100 times 1 over x. Now, most likely, this probably isn't like the greatest way to write this. This isn't the way you would, if you're checking your answer, you probably wouldn't see this. So most likely, we would write this as 30x squared minus 100 over x. Here is my derivative. Nothing necessarily wrong with this first line. It's just not how most of us would write that. Very cool. Next example, in part B, I have y equals natural log of x to the fifth plus e to the x minus natural log of e squared. This guy right here, I say, boy, natural log of x to the fifth, that looks a whole lot like natural log of x, but I have this power of 5 that I don't really know what to do with. How do I deal with this? This only says how to deal with natural log of x to the first. So I need to rely on these logarithm properties that I stated. Here's where we're going to need those. So I'm going to look, well, if I have x to some power, that looks an awful lot like this third property right here. This looks an awful lot like x raised to some power. So what happened to that power? What can I do with it? Well, I can bring that power, I can rewrite it as a factor. I can say, well, this says the same thing as 5 times natural log of x. Now again, be very careful. Notice I haven't actually taken the derivative. All I did here was rewrite the expression. So I don't really want to take the derivative of either of these other two terms, because then I end up with a situation where I've taken the derivative of some terms but not the derivative of others, and it's really, really easy to get mixed up. So I'm going to leave e to the x alone, minus natural log of e squared. Here I'm trying to trick you again. Remember, e is a constant, right? This is a constant. So I have a constant squared. This whole thing is a constant. You could actually type that into your graphing calculator right now and get an answer. If you look at the natural log of e squared, that's just going to be 2. So it's up to you. If you want to simplify it, you can. You don't have to. I do think it's probably easier to simplify it, because then in the next step, when I go to take the derivative, so I'm going to take the derivative of each one of these terms. 5 natural log of x, that'll be 5 times 1 over x, plus the derivative of e to the x, we said that was just e to the x. Derivative of negative 2, though, that's just plus 0, or I guess in this case minus 0. So I would say this is equal to 5 over x plus e to the x. I think simplifying this term right here is really nice, because otherwise you're going to be stuck asking yourself, well, how do I take the derivative of this? And it's really easy to make a mistake and think that it looks like natural log of x. Natural log of x is a very different thing than natural log of e. So we just want to be careful that we recognize the difference between those two things. A lot of subtleties in this section. A couple more here. I have y equals x to the fourth minus natural log of x to the fourth. So here in this case, again, I see this x to the fourth inside of my logarithm. I want to use that power rule. I want to use this guy right here. So I'm going to say y equals x to the fourth minus, I'm going to bring that 4 down, 4 times natural log of x. Now I haven't taken the derivative or anything like that here, so I still need to take the derivative. So let's do that. Y prime will be 4x cubed minus 4 times derivative of natural log of x. That's going to be 1 over x. So I've got 4x cubed minus 4 over x. Let's see, lastly right here, y equals 8 natural log of x minus 2x to the fifth minus 6e to the x. Doesn't look like I need to rewrite anything here. I can just hop in and take the derivative. So y prime will be 8 times derivative of natural log of x, that's 1 over x, minus 10x to the fourth, minus derivative of 6e to the x. We said that constant multiple right here, that 6 isn't going to have a dramatic impact. We just multiply our derivative. Oops. So it'll be 6 times e to the x. There is our derivative. So just keep an eye out for when you might need to be using these properties. Right now, this third one, this is the one that we're going to need to use most often. There may be a couple of instances in which case we might want to use this first or the second one, but really it's that third one that I want to focus the most on. Once we get to a later section, I want to say once we get to 3.4, we won't necessarily need these logarithm properties, but for right now, this is the only way for us to take the derivative of these types of functions. So here I want to continue our practice. I want to do one more example here, because what comes after this? Oops, yeah, we'll do one more example here. Find the equation of the tangent line of f of x equals 1 plus natural log of x to the fourth at x equals e. So let's see here. I want the equation of the tangent line. I've got an x value, which means I still need a y value. I still need a slope if I want the equation of a tangent line. So it's up to you how you want to approach these. You can find the y value first and then you can find the slope, or vice versa. It really doesn't matter. Let's find the y value first. Why not? If I want to find the y value first, I'm going to take the x value that was given to me, which is e in this case, and I'm going to plug that into my original function, which is 1 plus natural log e to the fourth power. Here you can use some properties of logarithms, or you can just rely on your calculator. You should have 1 plus, for my y value here would be 5. This is my y value. So y equals 5. So I have my y value. I need now my slope. I need m. So if I want the slope of the tangent line, I need the derivative. But I can't take the derivative of this term as it's currently written because I have that x to the fourth there. I need to use that third property of logarithms again. So I'm not going to take the derivative here. I'm going to just rewrite it. F of x is 1 plus 4 natural log of x. Now this term is written in a form that I can take the derivative of. So f prime of x will be, let's see, derivative of 1, that's going to be 0. I have 4 times natural log of x. That's going to be 1 over x, which is 4 over x. So I still need the slope of the tangent line here, which means I still need to take this x equals e and plug that into my derivative. I need to take that and plug it in down here. So let's do that. F prime of e is equal to 4 divided by e. And sure, you could get a decimal approximation, but where's the fun in that? We're just going to leave this, I think, as 4 over e. That is my slope. That's my m. So m is 4 over e. At this point, we have our x value, we have our y value, we have our slope. We've got everything we need, so we can go ahead and write the equation of our tangent line. Y minus my y coordinate is 5 equals m, that's 4 over e, times x minus my x coordinate is e. We can solve this for y pretty quickly if we distribute 4 over e. Y minus 5 equals 4 over e times x. If I look for these two terms, e is going to cancel. I'll just be left with minus 4 here. And then adding 5, I have y equals 4 over e times x plus 1 after I add that. So there is my equation of the tangent line. One thing that I just want to make a quick note of, this term right here, just be careful about how you write that. You can write it as I've written it, which really kind of looks like 4 over e times x, or you could write that as 4x over e. You cannot write that as 4 over e times x. If you put that x in the denominator, that's not the same as the other two, so just be very careful about how you write that. In the next video, we're going to take a look at, okay, we've looked at e to the x, but what if I have, say, 2 to the x? There's infinitely other cases. How do I deal with those? So we'll talk about that in the next video.